Welcome to the Future of Us Bookcast, your gateway to insights shaping our future. Today, we're undertaking an extensive look into a book that, honestly, fundamentally reshaped how many of us understand modern power, competition, and definitely technological progress. It's Chip War, The Fight for the World's Most Critical Technology by Chris Miller. Miller teaches international history at Tufts University's Fletcher School. He's also a visiting fellow at AEI, and he's really given us this monumental history lesson that feels incredibly relevant, like right now, to the headlines you see every day.
Absolutely. And the central idea, the thesis of this book, it's pretty provocative, and it's why we really wanted to dig into it for you. It's that semiconductors, these tiny chips, they basically determine the shape of international politics, they structure the global economy, and maybe most critically, the balance of military power. I mean, if you're trying to understand the rivalry between the U.S. and China today, the real battleground isn't just, trade tariffs or shipping lanes. It's fundamentally about who controls microchip technology.
That's such a powerful parallel the book draws. It reminds us that, say, World War II, a generation or two ago, was largely defined by brute force materials. How much steel, how much aluminum could you produce? But the conflict we're sort of in now, this current struggle for global influence, it might hinge entirely on computing power and who controls the tech that makes that power possible.
Yeah, and Miller sets the scene for this to grasp the scale just brilliantly. He opens with this image. Imagine the USS Mustin, a U.S. Navy destroyer, sailing through the Taiwan Strait, a really sensitive area. And this ship is just bristling with computerized weaponry. Everything, from radar to missile guidance, relies on these advanced microprocessors.
Okay, so you have this projection of military might.
Right. But at the exact same time, U.S. leaders back in Washington are intensely preoccupied with a Commerce Department rule. It's called the Entity List. And this rule restricts transferring American chip technology to Chinese companies.
Wow, so the tension is right there. The military depends completely on these tiny circuits for its precision advantage. Yet the supply chain that makes them is so complex, so maybe fragile, that a bureaucratic rule about IP carries enormous geopolitical weight.
Exactly. It shows you perfectly why Miller calls the chip the world's most critical resource.
And it's something you, the listener, interact with constantly, right?
Yeah.
Probably without even thinking about it.
Oh, constantly. Chips are genuinely everywhere. We're not just talking about your phone or your laptop, obvious examples. Think automated vehicles, industrial controls, medical equipment, and yes, military hardware like armed drones. The book points out that even a typical modern car has something like $1,000 worth of chips inside, controlling everything from the engine to the airbags to the infotainment system.
Right. So let's talk about that scale of production for a second, because the numbers are just mind-boggling. You mentioned TSMC, Taiwan Semiconductor Manufacturing Company. We'll definitely be talking a lot more about them later. They really define industrial power in this century.
They absolutely do. Take the example Miller uses. The A14 chip in the iPhone 12, okay? That single chip, tiny thing, has 11.8 billion transistors etched onto it.
Billion. Would it be?
Billion. Now, TSMC, in just a few months of production for that one single chip model, fabricated well over 1 quintillion transistors.
Okay, wait. Quintillion. That's a one with 18 zeros.
18 zeros. It's almost impossible to comprehend. Miller makes this staggering point. Last year, the chip industry produced more transistors than the combined quantity of all goods produced by all other companies in all other industries throughout all of human history.
That can't be right. Seriously.
It sounds hyperbolic, but it's the reality of semiconductor manufacturing scale. This isn't some niche technology, it's the bedrock. The industrial foundation the entire modern world is built on.
Okay, so to understand how we got to this quintillion transistor reality, we have to go back to the beginning where the book starts, with the urgency, the need for computation that came out of World War II, Chapter 1, From Steel to Silicon. It traces how warfare basically kick-started this whole search for computational power.
Yeah, the core argument here is that the drive for better calculation methods was massively accelerated by military necessity. I mean, calculation isn't new, right? The Babylonians had the abacus centuries ago. But by the 1930s, governments, militaries, businesses, they relied on human computers, often teams of women with slide rules or these really clunky mechanical calculators.
And the military especially ran up against the limits of those mechanical solutions pretty fast. The book talks about air forces developing these incredibly complex mechanical bomb sights, where a bombardier is turning knobs, inputting wind speed, altitude, trying to adjust metal levers and glass mirrors to hit a target from thousands of feet up.
And the results, they were terrible, just awful. When American bomb sites were actually used over Germany, something like only 20% of the bombs fell within 1,000 feet of their target.
20%.
20%. So the war, Miller argues, wasn't decided by precision at all. It was decided by sheer overwhelming quantity, just dropping masses of bombs and shells. They desperately needed faster, more complex calculations than gears and levers could ever provide.
So that's the shift. The foundational concept becomes moving away from physical gears to using electrical charges. And that brought in the vacuum tube.
Right. The vacuum tube looks kind of like a light bulb, was the first way to electrically switch current on, representing a 1, or off a 0 in binary logic.
A huge leap forward electrical.
A monumental leap, absolutely. But, as Miller explains, the technology had major drawbacks. Vacuum tubes were big, cumbersome, generated a lot of heat, they were slow, and crucially, unreliable. They burned out constantly. A single device doing simple math was literally the size of your fist. Building a complex computer meant tens of thousands of these things. You needed a warehouse, constant maintenance.
Just not practical for many applications, especially military ones needing speed and reliability.
Exactly. The military, in particular, needed a switch that was smaller, faster, cheaper, and more reliable. And that desperate need led them directly to the next big breakthrough.
Which brings us to Chapter 2, the switch. This chapter introduces the magic material, really, that makes everything possible. The semiconductor. Can you maybe outline what a semiconductor is and why it was such a game changer?
Sure. So semiconductors are materials, typically silicon or germanium. Normally, they act as insulators, they block electrical current, but the magic happens when you dope them, infuse them with really tiny, precisely controlled amounts of other elements like phosphorus or antimony. When you do that, they gain the ability to selectively conduct electricity under certain conditions. This means you can create a tiny, reliable switch with no moving parts, no filaments to burn out, and it doesn't generate nearly as much heat as a vacuum tube.
And this invention, this solid-state switch, is really tied to one figure in particular at Bell Labs, William Shockley. The book spends quite a bit of time on his personality, describes him as brilliant, but difficult.
Difficult is putting it mildly. Shockley was apparently utterly convinced of his own genius, very abrasive, and he led the Bell Labs team that eventually created the first working transistor. His personality really looms large in the early Silicon Valley story. Miller puts it very directly in the book. All his colleagues found Shockley obnoxious, but they also admitted he was a brilliant theoretical physicist.
That quote is great because it highlights something, right? That cutting-edge innovation isn't always this clean, harmonious process. It's often driven by these intense, sometimes difficult personalities.
Absolutely. It wasn't some idyllic research retreat all the time. There were clashes, egos. Shockley theorized this solid-state valve, what became the transistor, back in 1945. His key insight was that by applying an electric field to a semiconductor material, you could attract electrons to its surface and make it conductive, turn it on and off electronically.
Without heat, without burnout.
Exactly. This was the conceptual breakthrough, moving away from the fragile, power-hungry vacuum tube. This solid-state switch was precisely what the military needed to meet those rapidly growing computational demands of the Cold War.
Okay, so we have the transistor, the basic switch. But moving from one switch to putting many of them together on a single piece of material, that's the next leap. Chapter 3, Noyce, Kilby, and the integrated circuit. This is where the chip, the integrated circuit or IC, is really born. And this is what enabled miniaturization and, crucially, mass production.
Right, and this huge innovation actually happened almost simultaneously on two separate tracks, which is fascinating. First, you had Jack Kilby at Texas Instruments. He co-invented the IC in 1958. Kilby was working with germanium and figured out how to build not just transistors, but also resistors and capacitors all on one solid piece of material, connecting them with tiny gold wires.
But it was Robert Noyce, one of the co-founders of Fairchild Semiconductor, a really key early company whose invention truly unlocked the manufacturing potential, right?
Exactly. Noyce co-invented his version of the IC in 1959 using what's called the planar method, and this was the game changer for mass production.
How did the planar method differ? Why was it better for manufacturing?
Well, Kilby's initial design, while brilliant, was hard to build reliably in large numbers because you had to manually attach all those tiny wires between components. It was fiddly, prone to errors. Noyce's planar method, developed building on Gene Hoerani's work at Fairchild, allowed the entire circuit, transistors, resistors, capacitors, and the connections between them to be essentially etched or printed onto a flat piece of silicon using layers of chemicals and light, like photography.
Ah, so you could automate it.
Precisely. The whole process could be automated, repeated perfectly time after time. This meant you could produce chips in high volume with much lower defect rates and eventually much lower costs. That was the key to scaling up.
And the first big customers, the ones who really validated this new technology, were the military and NASA. The book highlights the Apollo program choosing Fairchild chips.
Yeah, think about the stakes there. The Apollo guidance computer, the brain that took astronauts to the moon and back, used Fairchild's integrated circuits. That computer weighed about 70 pounds, took up maybe a cubic foot of space, and it was 1,000 times smaller and lighter than the old ENIF vacuum tube computer that filled a whole room just 20 years earlier.
Incredible miniaturization.
And it proved these new chips could work reliably in the most demanding environment imaginable, outer space. That was a massive stamp of approval.
Meanwhile, Texas Instruments, with Kilby's invention, was focused on military applications, specifically guided missiles.
Right. TI won the contract for the guidance computer in the new Minuteman II missile. They basically promised the Air Force a computer using their ICs that would have twice the computational power, but weigh half as much as the previous version using individual transistors.
And for a missile, size and weight are everything.
Absolutely critical. An engineer who worked on that Minuteman II contract is quoted in the book, explaining the decision-making process. It was brutally simple. It was just a matter of size and weight. Smaller components meant the missile could fly farther, carry a bigger payload, or react faster. The military's relentless demand for miniaturization and performance provided that crucial early market, driving the initial volume needed to improve manufacturing and lower cost.
And this drive for smaller, more powerful components just kept accelerating. It led to probably the most famous prediction in tech history, Gordon Moore's observation in 1965.
Yeah, Moore, another co-founder of Fairchild, noticed this incredible trend. He predicted that the number of components, transistors, resistors, etc., that they could cram onto a single chip would roughly double every year for the next decade.
Which became known as Moore's Law.
Exactly. And it was an astonishingly bold forecast back then. Miller points out how futuristic Moore's prediction seemed in 1965. He was talking about things like an electronic wristwatch, home computers, maybe even personal portable communications equipment, stuff that sounded like science fiction.
Let's read that key assessment from the book. This forecast of exponential growth in computing power soon came to be known as Moore's Law. It was the greatest technological prediction of the century. It really set the pace, the expectation for the entire industry for 50 years.
But here's where Miller adds a really crucial layer, the economics. Moore himself later argued that Robert Noyce's aggressive price cuts at Fairchild were just as important in innovation as the technology itself.
How so?
Noyce made this incredibly bold move. He slashed the price of a particular integrated circuit from $120 down to just $15 in less than a year.
That's a massive drop. Why?
Because he understood that making chips cheap, really cheap, would open up entirely new civilian markets beyond just the military and NASA. And he was right.
So it wasn't just the Pentagon buying anymore.
Exactly. Suddenly, commercial computer companies like Burroughs could afford to use ICs. Burroughs placed a massive order for 20 million chips from Fairchild in 1966 alone. That was 20 times the total volume the entire Apollo program used.
Wow. And that volume.
That volume drove manufacturing efficiencies, brought costs down even further, which in turn funded the R&D to keep doubling the components, fulfilling Moore's Law. It became this virtuous cycle.
Driven by competition and, frankly, money.
Absolutely. The book really emphasizes this. Many of those early Fairchild engineers and managers, including Noyce and Moore, left to found their own companies, Intel being the most famous example. They saw the potential for immense wealth.
There's a great anecdote about an employee leaving Fairchild.
Yeah, on their exit questionnaire, when asked why they were leaving, they supposedly just wrote 4 words: "I want to get rich." That raw ambition, that decentralized, highly motivated, financially driven ecosystem was the engine of Silicon Valley, and it was the complete opposite of what was happening on the other side of the Iron Curtain.
Right, that relentless drive for innovation and wealth in the U.S. provides a stark contrast to the Soviet approach, which Miller covers next. They didn't have that ecosystem, they had bureaucracy.
Which leads us into part 2, looking at the Cold War competition and the beginnings of globalization in the chip industry.
Starting with the Soviet failure, Chapter 8 is titled simply, Copy It.
And the central argument is devastatingly clear. The Soviet Union's top-down, centrally planned copy-it strategy absolutely condemned its semiconductor industry to fall further and further behind. Miller argues forcefully that real innovation needs way more than just espionage and stealing designs.
And the whole Soviet effort literally started with theft.
Right. Yes, the story begins with a Soviet student, Boris Malin, returning from a trip to the U.S., specifically Pennsylvania, near TI's facilities, with a stolen Texas Instruments SN51 integrated circuit. He presents it to Alexander Shokin, the minister overseeing Soviet microelectronics.
And Shokin's reaction wasn't, okay, let's learn from this and innovate.
Not at all. He put the chip under a microscope, looked at his engineers, and gave a very direct order. The book quotes him. Copy it, he ordered them, 1 for 1. Without any deviations, I'll give you 3 months.
Wow. 1 for 1, no deviations.
And the significance, the truly chilling part, is that this mandate, just copy, don't think, don't improve, just replicate, became the defining philosophy for the entire Soviet semiconductor program for decades. They even went so far as to modify some of their chip-making machinery to use inches, following the American designs instead of the standard Soviet metric system, purely to make copying easier.
But even with the stolen designs, they just couldn't keep pace. Why not? What was the fundamental problem?
Miller identifies several critical barriers. First, and this is crucial for chip making, they consistently lagged in the quality and purity of the basic materials, the silicon wafers, the chemicals. You need incredibly pure materials for high-yield manufacturing, meaning getting a lot of working chips from each wafer. They struggled with that.
Okay, materials purity. What else?
Second, they faced major restrictions on accessing advanced Western manufacturing equipment. This was enforced by COCOM, the Coordinating Committee for Multilateral Export Controls, essentially a Western alliance agreement to prevent strategic technologies from reaching the Soviet bloc.
But they tried to get around those COCOM restrictions, didn't they? Through spying or shell companies?
They definitely did. They used front companies in neutral countries like Austria or Switzerland to try and buy restricted machinery illicitly. But, as Miller points out, you could maybe smuggle a few machines that way, but you couldn't acquire the entire cutting-edge production lines needed to operate at the scale and speed dictated by Moore's law. Let's read the quote from the book on this, because it really nails the issue. The Soviets could often bypass COCOM restrictions using shell companies in neutral Austria or Switzerland, but this pathway was hard to use on a large-scale basis. So Soviet semiconductor facilities regularly had to work with machinery that was less sophisticated and with materials that were less pure, producing far fewer working chips as a result.
So it wasn't just about having the design. It was about the tools and materials to actually make the chips reliably and in huge quantities. The percentage of good chips per wafer were much lower.
Exactly. That was the real manufacturing gap. And the third barrier, it was Moore's law itself. The cutting edge in the West was moving so incredibly fast, doubling capability every year or two. Stealing last year's design, which might take you months or years to copy anyway, was, as the book puts it, fundamentally a hopeless strategy. You were always falling further behind.
And culturally, it sounds like the Soviet system just wasn't set up for innovation in this field.
Not at all. Zelenograd, their attempt to create a Soviet Silicon Valley outside Moscow, lacked the vital ingredients: the risk-taking, the job-hopping, the venture capital, the intense financial motivation. In the Soviet system, career advancement came from being a loyal, compliant bureaucrat, not from being a disruptive innovator challenging the status quo. Their reliance on centralized planning and just copying what the West did yesterday ensured they were permanently lagging behind the dynamic, decentralized, profit-driven engine of Silicon Valley.
So while the Soviets were stuck trying to copy yesterday's tech, the U.S. industry was already taking another huge step offshoring assembly to cut costs. This is Chapter 10, Transistor Girls. Miller's argument here is that keeping up with Moore's law wasn't just about shrinking transistors. It also required finding cheaper and larger pools of labor for the assembly part of the process.
Yeah.
This kicked off the globalization of the supply chain.
And the driving force behind this relentless cost-cutting was Charlie Spork, the famously tough CEO of National Semiconductor. Spork was apparently obsessed with efficiency and, critically, with keeping labor unions weak or non-existent to keep wages down. See, the early stages of chip assembly, physically cutting the silicon wafers into individual chips, mounting them, bonding tiny wires to connect them, were very manual, very labor-intensive. So Spork needed cheap hands, lots of them.
And initially, he looked within the U.S., right?
Right.
Trying places like Maine or even the Navajo Reservation in New Mexico.
He did. He set up plants there looking for lower wages in places less likely to unionize. But even those domestic locations quickly proved too expensive compared to what was becoming available overseas in Asia.
Who made the first move offshore?
Robert Noyce at Fairchild actually invested in assembly facilities in Hong Kong first, where wages were incredibly low, maybe 25 cents an hour, like a tenth of the U.S. average at the time. Spork saw that and immediately followed suit, really pushing this offshoring trend aggressively. U.S. chip companies started moving their labor-intensive assembly operations to places like Singapore, where the government under Lee Kuan Yew had, as the book notes, pretty much outlawed strikes and strong unions, and later to Penang, Malaysia.
And this early wave of globalization, decades before the term became common, had really significant geopolitical consequences, didn't it? It laid the groundwork for the Asia-centric supply chains we see today.
Absolutely. And some leaders in Asia saw this strategically. Taiwan's key economic planner, KT Lee, was instrumental in persuading Texas Instruments to set up assembly operations in Taiwan back in 1968. For Lee, this wasn't just about jobs or economic development. He saw it as a crucial security move for Taiwan, which faced constant threats from mainland China.
How so? How did chip assembly link to security?
Lee had this incredibly shrewd insight. He understood that pure military alliances might be unreliable, but economic interdependence in a critical industry, that could create a powerful incentive for the U.S. to care about Taiwan's fate. He articulated the strategy very clearly, reasoning, as the book quotes, Americans who weren't interested in defending Taiwan might be willing to defend Texas Instruments. It established this idea that embedding Taiwan deeply into the vital tech supply chain could be a powerful deterrent, a silicon shield.
Fascinating. Okay, so moving forward into the 1980s, the main competitive threat in chips shifted. It wasn't the Soviets anymore. It was America's ally, Japan. Japan came to dominate the market for a specific type of chip DRAM, the memory chips used in computers. Chapter 16, At War with Japan, describes this period as a brutal economic conflict.
Yeah, this was a really tough time for Silicon Valley. Japanese companies, huge conglomerates like Toshiba, Fujitsu, NEC, were playing a different game. They were backed by patient capital from Japanese banks, had strong government support through industrial policy, and benefited from a relatively protected domestic market. They invested massively, about 60% more in new production equipment than their U.S. rivals during this period. This allowed them to achieve huge economies of scale and, critics argued, to dump memory chips onto the U.S. market below cost to drive American firms out.
And it worked, didn't it? U.S. companies really struggled in the DRAM market.
It was brutal. The memory chip business became heavily commoditized, a race to the bottom on price. Intel, the company that had actually pioneered GRAM technology, saw its market share just collapse. It fell to something like 1.7%.
Yeah.
Eventually, Intel made the painful decision to exit the memory market altogether and bet the entire company on microprocessors.
You can feel the desperation from the U.S. executives at the time. Charlie Spork again?
Spork was incredibly vocal. He saw parallels to how the U.S. consumer electronics industry, like TVs, had been decimated by Japanese competition earlier. He famously declared, "We're at war with Japan," Spork insisted, "not with guns and ammunition, but an economic war with technology, productivity, and quality."
At war with Japan. That really captures the mood, the feeling of being under siege in Silicon Valley. They felt they were competing not just against companies, but against Japan, Inc.
Right, and there was real frustration about market access, too. While Japanese firms could sell freely into the large U.S. market, American chipmakers found it incredibly difficult to sell into Japan. Major buyers there, including the government-owned telecom giant NTT, overwhelmingly favored domestic Japanese suppliers. This asymmetry cost U.S. firms billions in potential sales.
So this period exposed a potential weakness for the U.S. model, right? Great at innovation and startups, but maybe losing the edge in high-volume, low-cost commodity manufacturing.
Exactly. There was a real fear that the center of gravity for the entire semiconductor industry was shifting across the Pacific, and that the U.S. might lose control over this foundational technology.
But the book is careful to point out it wasn't just about Japanese competition. Chapter 17, titled Shipping Junk, argues that the U.S. decline in some areas was also due to major failures within American companies, especially in making the crucial tools needed for chip manufacturing, specifically lithography equipment.
Yeah, this is a critical point. Before we dive into the failure, let's just quickly redefine lithography for everyone listening. This is the absolute heart of chip making. It's the process of using light, shown through patterns called masks, to literally etch or carve the microscopic circuits onto the silicon wafers. It's like incredibly precise, multi-layered photography.
And as transistors get smaller and smaller, following Moore's law, this lithography process becomes exponentially harder and more important. You might repeat this layering process dozens of times for a complex chip.
Exactly. And the U.S. actually had a world leader in this critical lithography technology early on, a company called GCA Corporation. They were pioneers in developing the essential stepper technology machines that precisely move the wafer step by step to expose each individual chip pattern. They were at the forefront.
So what went wrong at GCA if they had the leading tech?
It seems to be a classic story of corporate hubris and mismanagement, according to Miller's account. Under its CEO, Milt Greenberg, GCA became overly focused on rapid expansion and boosting its stock price, apparently neglecting the painstaking, relentless focus on quality and precision that lithography demands. Remember, these machines are working at the nanometer scale. They are incredibly sensitive. Miller mentions an anecdote where even a tiny change in air pressure inside the factory caused by a thunderstorm outside could distort the light patterns enough to ruin the chips.
That's incredible sensitivity.
It is. But GCA's leadership, caught up in growth targets and stock options, reportedly wasn't listening carefully enough to their own engineers about quality control or, crucially, to their customers, the chip makers who were actually using these machines.
Which led to that damning phrase from the chapter title.
Exactly. Customers started complaining that GCA was shipping junk. The machines were unreliable, didn't meet specifications. GCA became arrogant, unresponsive.
And the consequences were severe for the U.S. position.
Devastating. While the U.S. government and industry were debating trade policy and how to counter Japanese subsidies, GCA's failures effectively handed a huge chunk of the vital lithography market to its Japanese competitors, primarily Nikon and Canon, who were listening to customers and focusing relentlessly on quality and reliability.
So the U.S. share of this critical equipment market just plummeted.
From around 85% in 1978 down to just 50% only a decade later. It was a self-inflicted wound. It showed that having the best ideas isn't enough. You absolutely need world-class manufacturing execution and quality control, and the U.S. in this critical area lost that edge.
Okay, so this sense of crisis, losing the DRAM market, fumbling in critical equipment like lithography, it forced a reaction, right? The U.S. government couldn't just stand by. Chapter 19, Death Spiral, covers this period where the U.S. government realized chips weren't just another product, they were a fundamental strategic commodity.
Exactly. This was the moment Silicon Valley, after years of wanting the government out of its hair, realized it needed Washington's help again. Jerry Sanders, the outspoken founder of AMD, really drove this point home. He started publicly comparing semiconductors to the crude oil of the 1980s. Now, he wasn't saying the Navy should go protect chip factories, but he was deliberately evoking the memory of the 1970s oil shocks. He was warning Washington, if the U.S. becomes dependent on foreign sources for this critical input, we face the same kind of economic and strategic vulnerability.
A powerful analogy for policymakers.
Very effective. And the response was twofold. First, the industry got organized, forming the Semiconductor Industry Association, SIA, to lobby effectively in D.C. Second, the government and industry collaborated to create a research consortium called Semitech.
Semitech. Its explicit goal was to revitalize American semiconductor manufacturing, right? Pooling resources.
Yes, and they quickly zeroed in on the biggest problem area. Bob Noyce, who was instrumental in setting up Semitech's strategy, explained their funding priorities very simply. Lithography research got 51% of Semitech's budget because, as Noyce put it, it was half the problem the entire U.S. industry was facing.
So a clear strategic focus on regaining control over those critical manufacturing tools.
Absolutely. They knew they had to fix the lithography gap that GCA had created.
But amidst these struggles, there were some American success stories, right? Not everyone was failing. The book highlights Micron technology.
Yeah, Micron, based in Idaho, famously part-funded initially by the potato billionaire J.R. Simplot, managed to survive and even thrive in the brutal DRAM memory market where giants like Intel had given up.
How did Micron do it? What was their secret?
According to Miller, Micron's success wasn't necessarily about groundbreaking new chip designs. It was about ruthless efficiency and innovation in the manufacturing process itself. They were relentless about simplifying production steps and cutting costs. For example, they figured out how to redesign their furnaces to bake 250 silicon wafers in a single load, whereas the industry standard at the time was maybe 150 wafers.
Okay, seems like a small detail.
It seems small, but when you make dozens of those kinds of incremental improvements across the entire complex production flow, the cost savings add up dramatically. That relentless focus on manufacturing efficiency gave Micron the cost structure it needed to compete head-on with the Japanese giants and survive the DRAM price wars when almost everyone else in the U.S. bailed out. It showed manufacturing prowess could still be an American strength.
Okay, so Semitic is trying to fix the tool problem. Micron is showing manufacturing grit. This leads into the 1990s and Chapter 28, which has this triumphant title, "The Cold War is Over and You Have Won." This chapter argues the U.S. actually recaptured clear technological leadership in semiconductors during the 90s. But crucially, not by winning back the DRAM market. Instead, they pivoted.
Exactly. The U.S. effectively sidestepped the commoditized memory battle and focused on dominating the new, high-value battleground, microprocessors, the brains of the booming personal computer revolution. And Japan largely missed this shift.
Why did Japan miss it? They were so dominant in memory.
Miller points to two critical failures in strategic vision by the big Japanese firms. First, they mostly failed to recognize the sheer scale of the PC revolution that Intel was fueling. Only one major Japanese company, NEC, even tried seriously to enter the microprocessor market, and they ultimately failed to compete with Intel's x86 architecture.
Okay, missed the PC microprocessor wave. What was the second miss?
Perhaps even more damaging in the long run, they missed the boat on NAND flash memory. This technology, which became the standard for storage in everything from USB drives to smartphones to SSDs, was actually invented by a brilliant engineer named Fujio Masuoka working at Toshiba.
Invented at Toshiba. But Toshiba didn't capitalize on it.
Unbelievably, no. Masuoka's bosses at Toshiba reportedly didn't see the potential, didn't invest significantly in it. They were focused on their existing DRAM business. So Masuoka eventually left, and companies like Samsung and later Apple reaped the rewards of his invention.
Wow. So Japan missed two massive shifts, microprocessors and flash memory.
They did, and because of these strategic errors, Japan's overall semiconductor market share, which had peaked near 90% in the late 80s, just collapsed. It fell all the way down to around 20% by 1998. Meanwhile, Intel, under Andy Grove's Only the Paranoid Survive leadership, had ruthlessly restructured, abandoned memory, and built an absolute fortress around the microprocessor market that lasted for decades.
And the definitive proof of this regained U.S. tech supremacy came not in the market, but on the battlefield, right? The 1991 Persian Gulf War.
Yes, the Gulf War was the first major, visible demonstration of the success of the U.S. offset strategy. Just to remind listeners, the offset strategy is the military doctrine focused on using superior technology in this case, silicon-based precision and information processing to overcome an adversary's advantage in numbers, like tanks or troops.
And the stars of that war were the precision-guided weapons, like the paveway laser-guided bombs. Their accuracy was revolutionary compared to bombing in Vietnam or WWII.
Absolutely revolutionary. And the media immediately grasped the significance. Military analysts were explaining it clearly at the time. One is quoted saying, "What's making all this work is weapons based on information instead of the volume of firepower. It was a fundamental shift in warfare."
And that famous New York Times headline really summed it up. It's the triumph of silicon over steel.
It perfectly captured it. And this technological dominance was so apparent, so decisive, that Miller recounts a stunning admission. As early as 1983, a top Soviet military leader, Marshal Ogarkov, had apparently told an American journalist off the record, effectively conceding the technological race. "The Cold War is over and you have won." And he specifically cited the Soviet Union's inability to keep pace with the West in microelectronics. Their masses of tanks and troops were becoming increasingly irrelevant against smart, silicon-powered weapons.
Incredible. So the U.S. is back on top technologically, but then the structure of the industry itself undergoes another massive transformation driven by one visionary individual. This brings us to Chapter 37, Morris Chang's Grand Alliance and the rise of TSMC and the foundry model.
Yes, Morris Chang is a truly pivotal figure. A longtime veteran of Texas Instruments, he was recruited by Taiwan's government by KT Lee, in fact, the same person who brought TI to Taiwan decades earlier to build a new kind of semiconductor company. Chang founded TSMC, Taiwan Semiconductor Manufacturing Company, in 1987, and his core idea, his foundational concept, was revolutionary: the pure-play foundry model.
Pure-play foundry. What does that mean exactly?
It means TSMC would only manufacture chips that other companies designed. Crucially, TSMC committed to never designing or selling its own branded chips. It would be a neutral factory for hire for anyone.
Why was that neutrality so important?
Because it solved a huge problem for a new wave of companies that were emerging, the fabless semiconductor firms. These were companies like NVIDIA, Qualcomm, Broadcom that focused purely on designing innovative chips, but didn't have the billions of dollars needed to build their own cutting-edge factories or fabs.
So they needed someone they could trust to manufacture their designs without stealing them or competing with them?
Precisely. Before TSMC, a fabless company might have to go to an integrated manufacturer like Intel or TI to get their chips made, but they always risked that manufacturer becoming a competitor or prioritizing their own products. TSMC offered neutral, reliable, state-of-the-art manufacturing capacity to everyone. This dramatically lowered the barriers to entry for chip design innovation. Fabless companies could focus all their resources on R&D and design, knowing TSMC would handle the incredibly complex and expensive manufacturing.
And this fueled a huge wave of innovation, right, in graphics, mobile communications.
Absolutely. It unleashed the creativity of hundreds of specialized design firms, driving progress in mobile phones, graphics processors for gaming and AI, networking chips, and much more.
Chang called this ecosystem the Grand Alliance. What did he mean by that?
He saw TSMC not just as a factory, but as the central hub coordinating a vast network. The chip designers, its customers, the companies providing specialized intellectual property, IP blocks, the equipment makers like ASML, the material suppliers. Because TSMC was neutral and focused purely on manufacturing excellence, it became the trusted coordinator for this entire complex global ecosystem. Everyone could align their roadmaps and investments around TSMC's capabilities.
And the economic power of this cooperative model became immense.
Huge. Chang himself highlighted this advantage over the old integrated model. The book quotes him bragging, quite rightly. The combined R&D spending of TSMC and its 10 biggest customers, he bragged, exceeds that of Samsung and Intel together.
That's a stunning statistic.
Yeah.
It explains how this distributed collaborative model, centered on TSMC, started to outpace the R&D resources of even the biggest traditional players like Intel. TSMC's focus on pure manufacturing created this gravitational pull, concentrating the industry's leading edge in Taiwan.
Which sets the stage for the modern era, where manufacturing the most advanced chips has become concentrated in just a few hands, creating new kinds of choke points.
Right. Part 4 looks at these modern choke points, starting with the technology needed to keep Moore's Law alive, EUV lithography. Chapter 39 is just titled EUV. Miller argues here that pushing miniaturization further led to this incredibly complex technology, extreme ultraviolet lithography, and concentrated an absolutely irreplaceable manufacturing choke point in one single company, ASML in the Netherlands.
Yeah, Moore's Law eventually ran into hard physics. For decades, chip makers used deep ultraviolet, DUV light, with a wavelength around 193 nanometers for lithography. But to etch features reliably below, say, 10 nanometers, you needed light with a much, much shorter wavelength.
And that required moving to extreme ultraviolet, or EUV, with a wavelength of just 13.5 nanometers. But making light at that wavelength, it's not like flicking on a special light bulb, is it?
Not even close. It's one of the most complex machines ever built by humans. Generating EUV light reliably and powerfully enough for mass production is an insane physics challenge. The solution ASML and its partners developed involves firing powerful lasers at unimaginably tiny droplets of molten tin, each about 30 millionths of a meter wide, inside a vacuum chamber. These tin droplets are shot through the chamber at high speed, and the laser hits each one twice, first to flatten it, then a microsecond later to blast it into a superheated plasma.
Plasma. Like hotter than the sun.
Yes, the plasma reaches temperatures many times hotter than the surface of the sun, and it's this intense plasma explosion that emits the specific 13.5 nanometer EUV light needed. And they have to do this 50,000 times per second, hitting droplet after droplet with perfect precision just to generate enough usable light.
That sounds completely science fiction. The engineering challenge is immense.
It's staggering. And this incredible complexity is why only one company in the world, ASML, headquartered in the Netherlands, has managed to successfully commercialize and mass-produce these EUV lithography machines. They have a total monopoly on the critical tool needed for manufacturing the most advanced chips.
And ASML itself relies on a very specialized global supply chain for key components.
Absolutely. The supply chain for an EUV machine isn't just global, it's highly specialized and often monopolistic itself. ASML depends critically on a company called Cymer, based in San Diego, California, to make the incredibly complex laser-driven light source. And they depend on the German optics giant Zeiss to make the multi-layered reflective mirrors needed to focus and direct the EUV light. The book mentions the astonishing precision required for these mirrors. If one was scaled up to the size of Germany, its largest bump or imperfection would be only 1/10 of a millimeter high. They are essentially the smoothest objects ever created by humans.
Wow. So you have irreplaceable components coming from the US and Germany, assembled into a machine only made in the Netherlands. That's concentration.
extreme concentration. Each EUV machine costs well over $100 million, sometimes closer to $200 million now. It contains almost 500,000 components, and they are so complex that they require ASML's own personnel to be stationed on-site at the customer's chip fab for the entire operational life of the machine, just to keep it running.
So the cutting edge of manufacturing hasn't really been globalized in the sense of being spread out. It's become radically monopolized, with ASML holding the ultimate key.
Precisely. It's a single point of failure, technologically speaking.
Which makes the story of Intel's struggles even more striking, because Intel was actually a key early funder of EUV research, wasn't it? Andy Grove made a big bet on it way back. Chapter 41, How Intel Forgot Innovation, digs into why Intel, despite huge spending in that early insight, lost its manufacturing lead.
It's a really sobering story. Intel was pouring over $10 billion a year into R&D through much of the 2010s. That was often more than TSMC and Samsung combined, and yet they fell behind technologically. It looks like a classic case of the innovator's dilemma.
The innovator's dilemma. That's when a successful company fails to adapt because it's too invested in its existing profitable business, right?
Exactly. Intel's existing business in by 86 microprocessors for PCs and data center servers was incredibly profitable. They had huge market share, high margins. When the smartphone revolution happened, driven by chips based on ARM architecture, Intel executives reportedly saw it as a lower margin, less attractive market compared to their core business.
So they hesitated to commit fully to mobile, even though it was clearly the next big wave.
They hesitated, they stumbled, they made half-hearted attempts. They couldn't bring themselves to potentially cannibalize their high-margin PC server business to chase lower-margin mobile chips aggressively. That hugely profitable by 86 moat they had built became, in effect, a strategic prison. They fundamentally missed the mobile transition, even though internal engineers had seen it coming.
So a strategic failure at the top. But what about on the factory floor? Their manufacturing execution also faltered, didn't it?
That was the other, perhaps even more critical, failure. Intel suffered repeated, multi-year delays in rolling out its new manufacturing processes, first at the 10-nanometer node, then at 7 nanometers. These delays were disastrous, allowing TSMC and Samsung to pull ahead. And crucially, Intel was very slow and struggled to effectively integrate EUV lithography into its production lines. By 2020, when TSMC already had about half of all the world's operational EUV machines running in its fabs, Intel was only just beginning to use them in high volume. Their whole manufacturing engine seemed to lose its edge. Its famous copy exactly discipline faltered.
And on top of missing mobile and stumbling in manufacturing, they also missed the boat on AI chips.
Absolutely. This might be the biggest miss of all in retrospect. Intel failed to recognize early on that graphics processing units, GPUs, which were being designed by fabless companies like NVIDIA primarily for gaming, had an architecture perfectly suited for the parallel processing needed in artificial intelligence training and machine learning.
Because AI involves doing lots of relatively simple calculations simultaneously.
Exactly. GPUs were designed for that kind of parallel workload to render complex graphics. It turned out they were ideal for training neural networks. NVIDIA seized this massive new market, becoming one of the most valuable companies in the world. And the irony, NVIDIA is fabless. They relied on Intel's rival, TSMC, to manufacture their cutting-edge AI chips.
So Intel missed mobile, fell behind in manufacturing, and missed the AI hardware boom. The consequences are huge, not just for the company, but geopolitically.
Miller spells out the stakes very clearly. Intel's struggles created a situation where, for the first time in decades, there is a serious risk that there won't be a single U.S. company or a single facility outside of Taiwan or South Korea capable of manufacturing cutting-edge processors. Think about that. The entire U.S. military advantage, the entire U.S. tech economy, increasingly reliant on foundries located in just two politically sensitive locations in East Asia for the most advanced silicon, that's a precarious position.
Which leads us directly into the final part of the book, focusing on the current AI and geopolitical dimensions of the chip war. Chapter 42, Made in China. This details China's massive, state-driven effort to achieve semiconductor independence precisely because they recognize this deep dependency on foreign technology.
Yeah, China's leadership views this reliance, especially on the U.S., as a fundamental strategic vulnerability, a critical bottleneck to their national rejuvenation and modernization goals. Xi Jinping stated it very clearly back in 2014. Without informatization, there is no modernization. He called for creating shock brigades and special forces to storm the passes of core technology research, especially semiconductors. This urgency led directly to the huge industrial policy initiative known as Made in China 2025.
The goal being to drastically reduce reliance on imported chips.
Exactly. But despite pouring hundreds of billions of dollars into this effort, the reality, as Miller lays out, is that China remains profoundly dependent across the entire semiconductor value chain. Overall, Chinese firms hold only about a 6% global market share in semiconductors, compared to nearly 40% for U.S. headquartered firms.
Where are the biggest dependencies for China?
They're critical. China relies almost completely on American electronic design automation, EDA software, the complex software tools made by companies like Cadence, Synopsys, and Mentor Graphics, now Siemens EDA, that are absolutely essential for designing any modern complex chip. China has less than 1% of the global EDA market. They also rely heavily on specialized chip designs and intellectual property cores, often from US or UK firms like ARM. They depend on critical manufacturing machinery from the US, Japan, and the Netherlands, ASML. And crucially, for cutting-edge fabrication, they still depend on foundries in Taiwan, TSMC, and South Korea, Samsung.
So, Made in China 2025 had these ambitious targets, like getting imported chips down from 85% to 30% by 2025. But hitting those targets for advanced chips seems incredibly difficult given these choke points.
It's proven incredibly difficult, especially at the leading edge. China has made progress in less advanced legacy chips and in areas like assembly and testing. But replicating the entire complex, interconnected global ecosystem for advanced chip design and manufacturing the EDA tools, the material science, the lithography is a monumental challenge that massive state funding alone can't easily solve, especially when facing export controls from the US and its allies. Trying to build a completely parallel, self-sufficient advanced supply chain is vastly expensive and slow.
Okay, so China's trying to catch up. Meanwhile, the competition is moving into new areas like 5G and AI. Chapter 47, The 5G Future, shows how control over these next-gen technologies hinges directly on who controls the most advanced chips.
Absolutely. On the civilian side, 5G networks promise much higher speeds and lower latency, but achieving that requires packing way more data into the limited radio spectrum. This demands incredibly sophisticated chips, advanced modems, complex radio frequency, RF transceivers, and it relies on computationally intensive techniques like beamforming, where the cell tower intelligently directs the radio signal specifically towards your device rather than just broadcasting everywhere. This requires immense real-time processing power that only the most advanced semiconductor nodes can provide efficiently.
And militarily, this ties into AI, right? Both the US and China see AI as the next frontier of warfare.
Definitely. China's People's Liberation Army, PLA, is actively pursuing what it calls intelligentized warfare, systematically integrating AI into command systems, autonomous drones, surveillance, cyber warfare, everything. The U.S. response is the third offset strategy. We talked about the first offset, nuclear weapons, and the second offset, precision-guided munitions, the triumph of silicon over steel in the 90s. The third offset aims to maintain U.S. military superiority through AI, autonomy, robotics, and advanced networking, all of which depend entirely on cutting-edge semiconductor performance.
And the case of Huawei really illustrates the global interdependence and the power of choke points, doesn't it?
It's a perfect example. Huawei, through its subsidiary HiSilicon, became capable of designing world-class, highly sophisticated chips for smartphones and 5G base stations. Really impressive designs.
They couldn't make them themselves.
Right. They relied entirely on TSMC in Taiwan to fabricate those advanced designs. Furthermore, even Huawei's most advanced 5G equipment still contain nearly 30% American-made chips, crucial components from companies like Texas Instruments, Analog Devices, Broadcom, Xilinx for things like power management, RF functions, and specialized processing.
So when the U.S. government put Huawei on the entity list and restricted its access first to U.S. components and then critically to any chips made using U.S. technology, which included TSMC's fabs.
It was devastatingly effective. It crippled Huawei's smartphone business and severely hampered its 5G ambitions globally. Even if Huawei could design a cutting-edge chip, they lost the ability to get it manufactured. It demonstrated the raw power the U.S. holds through its control over those key choke points: the EDA software, the manufacturing equipment components, and the core intellectual property.
But this reliance on commercial tech cuts both ways, right? The book mentions China exploiting U.S. openness.
It does. China has a national strategy called civil-military fusion, aiming to leverage commercial tech for military purposes. But Miller points out it often works in reverse. The PLA can simply buy advanced, commercially available U.S. chips, sometimes off the shelf or through distributors, and integrate them into their own weapons systems, like supercomputers used for modeling hypersonic missiles. The U.S. reliance on the speed and innovation of the commercial market, while powerful, creates this inherent vulnerability if rivals can easily access the same cutting-edge technology. Yet the fundamental equation remains what Bill Perry saw in the 90s. High tech works. The advantage comes from weapons based on information instead of the volume of firepower. Controlling the information edge is paramount.
Which brings us to the final chapter we'll discuss, Chapter 52, China's Sputnik Moment. This really looks at the fragility of the current system, the risks highlighted by recent events, and the potential future paths.
Yeah, it pulls together the current situation. It touches on the 2021 auto chip shortage, which caused huge disruptions. But Miller argues that shortage was widely misunderstood.
How so? Wasn't it a failure of the global supply chain?
Not exactly, according to the book. While it exposed fragility, the root cause wasn't primarily a breakdown in semiconductor production. In fact, the chip industry produced significantly more devices overall in 2021 than in 2020, about 13% more. The bigger issue was a demand shock and poor planning by the automakers. Early in the pandemic, car companies panicked and slashed their chip orders, thinking demand would collapse. When demand rebounded faster than expected, they found themselves at the back of the queue, as chip makers had already reallocated that capacity to booming sectors like consumer electronics and data centers. Combined with the automakers' reliance on lean, just-in-time inventory practices, it created a bottleneck for them, even as overall chip output was rising.
Okay, so more of a scheduling and inventory management failure than a fundamental production collapse. But the perception of fragility was powerful.
Hugely powerful, and the underlying risks are very real. China, for instance, continues to pour subsidies into building up its domestic chip manufacturing capacity, especially in older legacy nodes. Miller notes how during the strict Wuhan lockdown, workers at the memory chip maker YMTC were given special transport and housed on-site to keep production running, showing the national priority. This state-backed expansion means China's share of global fabrication capacity, particularly for less advanced chips, is projected to grow significantly, potentially reaching 24% by 2030. This won't give them leading-edge tech necessarily, but it will increase their leverage and importance within the overall global supply chain.
But the biggest risk, the ultimate geopolitical choke point, remains Taiwan. The concentration of advanced manufacturing there is just staggering.
It really is the focal point of global risk. The book paints a stark picture of what could happen if conflict, blockade, or invasion disrupted Taiwanese production, especially at TSMC. Miller estimates it would immediately take about one-third of the world's processing power offline, the chips that run our PCs, servers, smartphones. Building replacement fabs elsewhere would take years and cost hundreds of billions. The rollout of 5G, development of AI data centers, production of advanced cars, pretty much the entire engine of the modern global economy would grind to a halt or be severely crippled.
Given that catastrophic risk, it raises the question, why can't a country like the U.S., especially the Pentagon, with this massive budget, just build its own dedicated, secure, cutting-edge fabs to guarantee supply, ensure technological sovereignty?
That's the fundamental dilemma Miller explores. The sheer cost and complexity of building and operating a leading-edge chip fab today are astronomical, tens of billions of dollars just to build one, plus billions more annually in R&D to stay competitive. Even the Pentagon's vast budget, around $700 billion at the time of the book, isn't large enough to sustain dedicated, state-of-the-art military-only fabs. Why? Because semiconductor technology only advances rapidly when it has massive commercial volume to drive down costs and fund the next generation of R&D.
So military tech rides on the coattails of consumer tech.
Essentially, yes. The cutting-edge performance the military needs only becomes affordable and available because companies like Apple, NVIDIA, Qualcomm, and AMD are buying billions of chips for iPhones, gaming consoles, and data centers. Without that enormous commercial market absorbing the volume and funding the relentless pace of Moore's Law through companies like TSMC, the technology would stagnate or become prohibitively expensive, even for the Pentagon.
So complete technological autonomy in chips at the leading edge is basically impossible, or at least prohibitively expensive, for any single nation.
That seems to be Miller's conclusion. The cost is just too high. You need the scale of the global commercial market.
And this extreme concentration of capability, particularly in Taiwan, is paradoxically what gives the U.S. leverage through weaponized interdependence, right?
Precisely. Because the system is so concentrated and relies on key technologies where the U.S. still holds choke points like the EDA software needed for design and critical components within ASML's EUV machines, like that Cymer light source made in San Diego, the U.S. can exert enormous pressure. It can effectively deny rivals access to the most advanced manufacturing capabilities, as it did with Huawei. Miller calls these sanctions devastatingly powerful. The fact that the key enabling technology for EUV relies on a U.S. subsidiary gives Washington a crucial lever in the entire global system.
Okay, that's a lot to cover. Let's try to synthesize this incredible journey. We started with the urgent demands of World War II, pushing beyond mechanical calculators to vacuum tubes. Then the invention of the transistor by figures like Shockley. Then came the integrated circuit from Kilby, and crucially for manufacturing, Noyce et Fairchild, validated by the Apollo program and Minuteman missile, all governed by the relentless pace of Moore's law, which was driven as much by economics as physics.
Right. Then we saw the Cold War competition, where the Soviet copy-it approach failed against Silicon Valley's dynamic, decentralized innovation engine. We saw the U.S. industry respond to the fierce challenge from Japan in the memory market, partly through government help like Semitech, but also through internal grit like Micron's manufacturing focus, and critically by pivoting to dominate microprocessors.
Which led to the next paradigm shift. Morris Chang's creation of TSMC and the pure play foundry model. This unleashed fabulous innovation, but also concentrated the world's most advanced manufacturing in Taiwan.
And that brings us to today, where keeping Moore's law going requires the near-magical EUV technology, monopolized by ASML, creating an ultimate choke point. We see Intel struggling to regain its footing after strategic missteps, while China pours resources into catching up, facing U.S. export controls designed to maintain control over these critical choke points. The whole system rests precariously on the geopolitical stability of Taiwan.
It's an amazing narrative arc, so if you had to boil it down, what are the absolute key takeaways from Chip War that listeners should remember?
Okay, let's try. I think maybe 5 main points stand out. First, Moore's law wasn't just physics, it was economics. That exponential growth was fueled by fierce competition, the need for massive sales volume to recoup R&D, and billions in investment. It's an economic engine as much as a technological one.
Second takeaway. The big shift in industry structure over the last couple of decades was from those integrated companies that did everything, design to manufacturing, like old Intel or TI, to the specialized fabless foundry model, where designers like NVIDIA or Apple rely on manufacturers like TSMC. That specialization redefined innovation and concentrated manufacturing power.
Third, and this is crucial, cutting-edge manufacturing capability hasn't really globalized. It's monopolized. One company, ASML in the Netherlands, controls the essential EUV tool. That's a unique and powerful choke point in the global system.
Fourth point. America's military edge today absolutely depends on the commercial semiconductor industry and the stability of those supply chains, mostly in East Asia. Military tech advances because consumer tech pays for the R&D. There's no separating them at the cutting edge.
And finally, fifth, that concentration of the most advanced chip manufacturing, overwhelmingly in Taiwan, with South Korea also critical, represents arguably the single most dangerous geopolitical vulnerability in the world today. A disruption there would be catastrophic globally.
Those are stark takeaways. Looking forward, you mentioned the paradigm might be shifting away from just general-purpose computing.
Yeah, that's an interesting final thought Miller touches on. For decades, the focus was on making single CPUs faster and faster for general tasks. But maybe that's slowing. Instead, we're seeing the rise of specialized chips like NVIDIA's GPUs, originally for graphics, now powering the AI revolution, or Google's TPUs specifically for machine learning. These specialized architectures, often designed by fabless companies and made by TSMC, are making complex technologies like AI much more accessible and powerful, even if general-purpose CPU progressive quantum Moore's law slows down. So the nature of innovation might be changing too.
A fascinating possibility. Even as the geopolitical risks around manufacturing intensify, the types of chips driving the future might also be shifting.
It adds another layer of complexity to the whole chip war. The interdependence is deep, the choke points are real, and the future path is far from certain.
Thanks for tuning in to the Future of Us Bookcast. We hope you found inspiration in these ideas. Don't forget to subscribe and share. Together, we're co-creating the world of tomorrow.